my talk is in the interface between harmonic analysis and geometry of Banach spaces. So this, so I first introduce the setup for this work. So the first one is the first one is the so-called symmetric diffusion semigroup introduced by Stein. So this is a semigroup on a major space omega satisfying the following conditions. So TT is a contraction on a P for every P between 1 and infinity. So here by contraction I mean a linear operator of long less than or equal to 1. And of the second condition, the third condition. The third one is continuity, the stronger continuity of the semigroup. And this one is very important for this theory. So T is positive. That means so the operator TT maps positive functions, non-negative functions to non-negative functions. The last one is also important in Stein's theory as an operator on A2. So each TT is self-adjoint. Okay. So in this case, we will consider this square function, this so-called square function. So given any f in AP, so TT applies to f. So we get a function depending on t. So we take the derivative with respect to t, then we form this kind of square function. So this function is a very important function in harmonic analysis. Okay. So our aim is to compare the AP norm of f and that of this square function. So this square function is in general a measurable function. We want to know how to compute the AP norm of this square function by that of f. Okay. So this is the aim of Stein. He has a very beautiful book about the Littlewood-Paley-Stein, a small book. One of the two main results is now it's called the Stein inequality. I will present to you in the later. Another one is about the maximum function. So first I give you some examples. Okay, very classical examples. The first one is this. The classical heap of Poisson semigroup on RD, the Euclidean space of here. Delta is the classical Laplacian. And the second one is the OU, Ornstein-Uhlenbeck semigroup on RD again. But now RD is equipped with the Gaussian measure. And the generator of the semigroup is minus the Laplacian plus x times the gradient of on RD. The third one, there are many other examples of the third one is the so-called basic model of the second one, this so-called worksheet system. For this workshop, so this is the infinity dimensional hypercube. Okay, so we have the diagonal group with the normalized hard measure, and we have the so-called Rademacher function. This is coordinate function. Then we define the worksheet system. Okay, so we have this Fourier expansion. So we define this semigroup. This is also a very good semigroup. So this the number of the cardinal number of A. So this is also a very standard semigroup on the worksheet system. So all these semigroups are symmetric diffusion semigroup. Okay. So now I give you the Stein inequality. So Stein proves that in this case, you see this, the AP norm of the square function, in fact, is equivalent to the AP norm of the function f itself. Of course, we have to remove the fixed point space, the fixed point projection of the semigroup. You see this capital F of F is just the projection to the fixed point subspace of the semigroup. So you see, so if F is a fixed point, then the left-hand side, the derivative is 0. So the square function is always 0. So we have to remove this part. And moreover, in this equivalence, the two constants we have, so this is two-sided inequality. The two constants, both of them, depend only on the parameter P. Okay, so in the classical case, you see if TT is a Poisson semigroup on RD, so this is the classical Littlewood-Paley inequality. So nowadays, so this equivalent is called Littlewood-Paley-Stein inequality. Okay? And the Stein proves. So I just mentioned Stein has a small book, a red book. So one of the two main theorems is this one. Okay, the proof is very long and technical. So the main point is so Stein reduced so this inequality to martingale inequality by using this Rho-dimension theorem and then some complex interpolation machinery. Okay, machinery. The proof and also his proof produces the two constants, the dependent on P is exponential, very, very big when P, so this equivalence fails when P equal to 1 or P equal to infinity. So here P is strictly between 1 and infinity. So when P goes to 1 or to infinity, both constants blow up exponentially. Okay.
This is just in the proof, or it's known that it's go? It's known that it goes exponentially? Or?
Yes, the proof we reduce, but of course this...
Only the proof gives this?
The proof gives this, yes. In fact, some problem is still, for some constant in some case, is still open problem how to find the optimal order.
And this probably changes for one semigroup?
Yes, even for this one, so okay. I will mention this later. Okay, that coding improved, in some sense improved Stein inequality. So in Stein inequality, so the semigroup is supposed to be Markovian. That means, so TT, so maps the constant function 1 to constant function 1, but in coding uses another proof. He just need to suppose the semigroup is sub-Markovian. That means so the norm of TT on A infinity is less than or equal to 1. So the aim of this talk is to consider the vector value extension, so related to the geometry of Banach spaces. So now I consider a Banach space X, a general Banach space X. So we have this AP of function with value in X. So this is the X value AP space, and because the TT, each operator TT is positive preserving. So this TT extends to a contraction on AP of X. So we still have a semigroup of contraction on this vector value AP space. Okay, I just imitate the previous contraction of square function, replacing the complex the absolute value of complex lambdas by the norm of x. So we can still form the same square function, of course not for all f, but for some f, the dense subset of f in a P of x. So this is such that the partial derivative exists. Okay? So we still have a non-negative measurable function. So we want to compare again the epsilon of this square function and the epsilon of f for any f in the vector valued P space. Okay? For some p strictly between 1 and infinity, or for all p strictly between infinity. Okay? So this problem, the answer is in fact, is very easy. In some sense, it's very easy after some source. So we can show, in fact, in this case, this equivalence holds for the Poisson semigroup. For example, for the Poisson semigroup on a unity circle, if and only if X is isomorphic to a Hilbert space. Okay. So in one direction, the proof is very easy. So if, for example, if X is a Hilbert space, then we can just follow Stein proof to show this equivalence still holds. But the other direction is a little bit harder. In this case, we have to show X is of type 2 and also of cotype 2. Then by Quanhua theorem, X is isomorphic to Hilbert space. So I don't use the notion type or cotype in this talk. I will present to you some more, in some sense, stronger notion, martingale type and cotype later. So
what inequality holds and which one?
Both, in this case, both. One is, so I will mention later, just later. Okay, so in this case, you see this. So because the answer is very easy. So that means the story stopped here. But this, in fact, this is not true. In fact, just Sasha asked, we can consider only one of the two inequalities. So this equivalence is a two-sided inequalities. You will consider one of the two, then the family of Banach space X is much larger. So this is related to the so-called two uniformly exposed spaces, and for the lower estimate, and the so-called two uniformly convex spaces for the upper estimate. So this, you see this, because two uniformly exposed, both two here correspond to the index here. The index here to have the square function. But in the geometry of Banach space, we can consider more general Banach space, for example, Q uniformly smooth or Q uniformly convex. Just replace 2 by some other number Q. So I'm going to consider some general Q variation of this square function. Okay, so this is so before that, now I remind you the notion of type and cotype, but relative to martingales. The notion introduced by Bezier in the 80s. Okay, so the Banach space X is of martingale cotype Q if there is a constant C such that all finite X valued AQ martingales satisfy this inequality. So you see in this inequality, on the left-hand side, we have these differences of the martingales. So this, in some sense, is the discrete derivative. We should compare the left-hand side with the square function here, you see. So this is a square function. Okay, so this we take the derivative, then we multiply by t. So we consider this one. So this you see that you will consider this in this equivalence. We consider the upper estimate. We want to compute the AP norm of the square function, but for example, a Q norm of the function itself. Then we go back to, then we can come back to this martingale case. You see on the right-hand side, this is a Q norm of the martingale to power Q. On the left-hand side, we take the derivatives, the discrete derivatives. When we take to power Q, we form. So this is also a Q norm of some square function in some sense. Q variant of square function. So this is the so-called martingale cotype Q. So for the other inequality, the upper estimate, lower estimate. So if the reverse inequality holds, then X is said to be of martingale type Q. So we have type and cotype. Cotype corresponds to the upper estimate for the square function, and type to the lower estimate for the square function, for the square function in this case. Okay. So if you have never seen such a notion, in fact, the job. So this is I just explain to you the geometric meaning. So this, in fact, this famous theorem of Bezier, which states that X is of martingale cotype Q if and only if X admits an equivalent norm that is Q uniformly convex. Okay. And for the type, it corresponds to smoothness. Okay. So again, these two notions are very easy to understand by this generalization of the classical polygon identity. So you see in the here delta is a positive constant. Delta is strictly positive. Okay. In the classical case, so if X is a Hilbert space, so we have this so-called parallelogram identity for Q equal to 2. So you see, if Q is equal to 2 and delta is equal to 1, then we have the identity of both sides. Okay. Now we renex this identity to two inequalities. If Q is still equal to 2, then we have to allow some constant here. Then we get, for Q equal to 2, we get two uniformly convex and two uniformly smooth spaces. And for general Q, so this is just this corresponding to, in some sense, to two Q, martingale cotype Q and martingale type Q after two equivalent norm. Okay. So some facts. So I mentioned before. So if X is both two uniformly smooth and convex, then X must be a Hilbert space. Of course, the converse direction is true. Okay. And for example, some example, the usual AP space, any AP space, commutative or non-commutative AP set for the shortened P class. So for if P is strictly between 1 and infinity, then AP is minimal P2 uniformly smooth and maximum P2 uniformly convex. So in this case, you see then if for the cotype Q must be between 2 and infinity. For the type Q, the index Q is less than or equal to 2. Okay. So there's some examples. There are some many other examples. So from this example, so you can see the family of Banach spaces which are two uniformly convex is much larger than the Hilbert space. Okay. So now I go back to my semigroup case. Okay, again, so as I said before, now I can form some general square function replacing Q2 by Q, some index Q straight between 1 and infinity, and we find such a Q variant of the usual square function. Okay, usual square function. So you should compare this square function with the martingale case. You see, in this martingale case, you see, we remove the expectation, the integral here, then we form this sum, and to power 1 of the Q, we get the martingale analog of this Q variant of square function. So the two sides, from the semigroup side and the martingale side, both they are, in some sense, they are parallel and similar. Okay, the situation is very, very similar. So we have this general square function. So we now...
You wrote F is in LP, you mean F is in LQ?
F in LP. Q is fixed, QP are usually are two different. QP are different. So in fact, P value Q is fixed in my talk.
Okay.
So Q is fixed and P can vary from 1 to infinity. Okay. So you see, we in this case we want to compute the epsilon of this Q variant of F by the epsilon of F. Okay. So this is the upper estimate, so which is analog in some the notion of martingale cotype Q. Okay. In this case, the Banach space X is said to be of Newton cotype Q, of course relative to the semigroup. When the semigroup is given, so we have such a notion of Newton cotype Q. So Newton cotype of semigroup, which is analog of martingale cotype Q. And if the reverse inequality holds, then X is said to be of Newton cotype Q. Okay, so we have, again, this is the analog of the martingale case. Okay, so this is a quite older result I proved more than 20 years ago. So in the special case when the semigroup is the Poisson semigroup on the unity circle. Okay. So this is yes.
So just to make sure I understand. So the definition of using cotype Q, you ask the inequality to be true for every F and for every P.
No, relative to T.
Yeah, but what is the role of P here? It's for
P that can be, okay, I didn't mention
it's equivalent for
the equivalent for 1P and for all P.
Okay.
This is like in the martingale case is the same. For example, I'll take this one. In this definition of PZ, so this is P equal to Q. So think that Q is fixed, P varies. Okay. So this is for P equal to Q. You will have such inequality for P equal to Q. Then from the general theory of martingales, we have the same inequality. Of course, you have to further remove this expectation P for the so-called Q variant to power the sign to power 1 of Q. Then you can take the epsilon is the same. Okay. So this is the okay. Of course, the precise definition should be we should mention also the P in this definition. Okay. So in fact, the definition doesn't depend on P. Okay. So in this simplest case, this is a very classical semigroup on the unity circle. In this case, so we proved that X is of using cotype Q. Using cotype Q is equivalent to the martingale cotype Q, and also as well as for type case. Okay, the proof is already in some sense in some other some ideas of proof appear again in the latest work. I will present later. So using, for example, is using this probability theory and also the cardinal sigma singular individual operators. Okay, I will mention this in more detail later. Okay, in more general case. So this is a very classical case. Okay, in fact, in the semigroup theory, we have many semigroups which are not don't act on a P for all P between 1 and infinity. I just mentioned the definition of Stein of symmetric diffusion semigroup. You see in Stein theory. So you see in this definition, so TP is a contraction on a P. So for all P between 1 and infinity. Okay. But in analysis, many semigroup don't satisfy this condition. Some semigroup acts on a P just for a single P, string between 1 and infinity. Okay. And also in this case, there are two other conditions are crucial in Stein theory. This macrovianity and also this symmetry. So this is why the semigroup is called the symmetric diffusion semigroup. So we have such a symmetry. So T acts on A2 as a self-adjoint operator. And also T preserves the constant functions. Okay. So all these conditions are very essential in Stein theory. So we want we wish to extend this theory to a more general setup. So this is, so for example, now we consider only we fix one P. Now P is also fixed in some sense. Okay. We fix one P string between 1 and infinity. We consider a strongly continuous semigroup of possible contraction on a P. Okay. So P is fixed. So P is fixed. In this case, for example, we cannot talk about the macrovianity, because if the measure space omega is infinity, the constant functions are not in AP. Okay. Of course, we cannot talk about the symmetry, because P can be different from 2. So if P is different from 2, so we cannot consider the symmetry of the operator TT. So this is a very general situation. So such a semigroup of course admits a generator, so minus A, and we consider the so-called Poisson semigroup subordinated to TT. The Poisson semigroup in general is better than the semigroup itself. So just think about the hidden semigroup on a Euclidean space and the associated Poisson semigroup. Okay, semigroup. Then so this is the result I. In fact, I proved in just 3 years ago during the first year of the COVID. I just published this year online. So this is general result. For now X is a Banach space Q is fixed, and our semigroup is also fixed on one AP. Okay. So in this case, if X is of martingale cotype Q with Penguin type Q, then X is of Newton cotype Q relative to this subordinated Poisson semigroup. Okay. Then for any Banach space X is true, and for any semigroup TT, and the second part concerns the semigroup TT itself. Okay, so in this case we have to assume TT is analytic on AP, then the same statement holds for the semigroup itself. Yes.
So just to have in mind, what's an example of a semigroup that we only...
I will mention this, okay? So in this, the analyticity here is very important here, okay? So for some Banach space, so the extension is not analytic. In general, even in the scale case, such a group, if we don't, so of course, such a subgroup can be extended to AP. The x-valued AP is still a semigroup of contraction. Even in the scale case, if x is a complex number, so the semigroup can be not analytic. And analytic means the semigroup can be extended to a symmetric sector around R plus and analytic holomorphic functions. I will give you some example in the one. So this is about this analyticity of semigroup. So why? So I think that PT, the Poisson semigroup is better because, for example, this is one example. So this Poisson semigroup is always analytic on AP also. Okay, for any Banach space. Okay. Of course, P is strictly between 1 and infinity is fixed. However, so this is not true for the semigroup itself. Okay, this semigroup itself is some. So I give you some. This is the example of this. Okay, is the highly non-trivial example. So you see in this case, if the semigroup is diffusing semigroup and X is sub-reflexive, then the extension is analytic. In this case, in the scalar case, the AP, the TT is always analytic on AP for FAP, strictly between 1 and infinity. And the second one, you see this so the group, semigroup is quite, you see is good, a very good semigroup, and the Banach space X is sub-reflexive. That means an equivalent norm which is uniformly convex. Okay, but if we give a strong assumption on the semigroup, the semigroup is a convolution semigroup introduced by symmetric probability measured on a locally compact abelian group, then we can weaken the assumption on X, on the geometry of X. So now X needs to be only K-convex. K-convex means that X has a non-trivial type. A non-trivial type, so it's of type P, bigger than 1. So this super-reflexivity implies this K-convexity. Okay, so now the geometry condition is weaker. And I proved some years ago, if the semigroup is in this case, in our case, is just a positive contraction on AP for a fixed P, and X, in this case, we have to so the assumption on the semigroup is very weak. I think it's the weakest possible. But we have to assume the Hilbert space you see in this case. Okay, I think I forgot to mention also analytic. The semigroup itself, this one in the scale case is analytic. So TT, I forgot the analyticity here. So TT is an analytic semigroup of positive contraction on AP, and X is a complex interpolation space of Hilbert space and another Banach space. So this is so-called the sector Hilbertian space, so defined by BD. So this is also quite a big family of Banach spaces. So in this case, extension is also analytic. So in BZ series, so this is just is a calculation. Okay, if we have for any symmetrical diffusion semigroup, so the extension is analytic, then X must be subreflexive. In this case, this is also something is also a calculation. Okay, you have to assume that for a large family of semigroup, family without holes, then X must be superreflexive, and in the second case, X must be K-convex. For example, if you just take the washing system, okay, I mentioned before, the washing system I mentioned before, in this case, both converse direction holes. So all these are just, in some are just, in B the result, these are just calculation of superreflexivity and K-convexity. Okay?
Is there a similar characterization for given these spaces in terms of?
This is the problem for a single one. In fact, for example, my result is also one direction. You can ask the same problem for the converse direction. Okay. For converse direction, if you suppose this TT is any semigroup in some larger families than the converse holds. Okay. For example, if you this is true for, as I mentioned before, for the Poisson semigroup on unity circle or Poisson semigroup on Euclidean space or some other semigroup for Cauchy system or OU semigroup, some other. In fact, this is a very interesting problem we fix a semigroup with TT, then how to prove. Of course, we should suppose some additional assumption on the semigroup. Then we wanted to show the converse direction. Okay. So in this case, the semigroup should be quite, in some kind, at least the description of the semigroup should be quite large in some. Okay. So this in BZ case is the same for some for some particular semigroup, the converse, both converse are. Okay. I mentioned some previous null result. The first one is the scale case. So you see, I suppose TT is analytic. Okay, this now X, the balance space X is just the complex numbers. Okay, then we have this equivalence. So this we proved several years ago with H1 MAD. So this equivalence, so we extend Stein inequality to this more general setting, Of course, I mentioned before, so this equivalence improves upon Stein and Koenig result in some aspects. So first, we consider only one P. P is fixed, and we cannot assume Markovianity nor symmetry. Okay, nor symmetry. So this is much more general. And also come back to the Stein setup or symmetric diffusing semigroups, we proved the previous result many years ago with Martinez and Toria for the Poisson semigroup subordinated to a symmetric diffusion semigroup. So I mentioned that means for the first part of our main theory for the Poisson semigroup. So the problem for TT itself is subtle and was left open in our previous work. Okay. And also for the heat semigroup, you see this is a quite recent result. So the heat semigroup, so the answer is positive. Okay, the answer is positive, then this is proved by Thomas and Hausdorff some years ago. In fact, the work motivated me, in fact, gave me some motivation to come back to this theory. In fact, using some idea from their paper. So although they consider only this very special case, but some ideas work in a more general case. So finally, I solved. So this problem left in this work with Martinez and Toria for general symmetric diffusion semigroup. Okay. So the paper of now, my paper was published before the publication of their papers, but this work was directly motivated by their work. Okay. So all this are the result before the final one from very general case. Okay. So during my research on this work, I had many communication, email exchanges with Hausdorff. At first, in fact, I didn't care about the basic constant. Then Hausdorff asked me some question about the basic constant, and also he sent me his very recent in that time paper with Jung about some basic constant in this theory. In fact, Hausdorff used this theory to the approximation of Lipschitz maps, and also this theory is also useful for theoretical computer science. So after this email exchange with Hausdorff, and also after his questions on the basic constant, I continue to work on the basic constant. Now I want to give you some now the basic constant on this one. Okay, so I show you all the whole page. So now again, so I thought you mentioned, so this PT is a general semigroup, and PT is the superlative Poisson semigroup, and X. So we recall that now I consider only cotype case, and consider X. So this is the definition of the martingale cotype Q. So here we have a basic constant. Okay, the basic constant is denoted by MCQ. So C for cotype, Q for the index Q of X. Okay. So here we have a constant of martingale cotype Q. Then in our inequality, so in our using type inequality, we have also a constant. Okay, we have also a constant. This is the basic constant I denoted by alpha PQX. Okay. So this constant depends on PQX. So thinking Q is fixed, so P can vary. Okay, of course, in our case, in this case, P is also fixed. But if for example, if TT depends is a semigroup or contraction on a P for all P between 1 and infinity, then P can vary. Okay, so the optimal order of this constant is when P goes to 1 or P goes to infinity. In general, when P goes to 1 or infinity, this constant blow up. So now the aim is to determine the optimal order of this constant. Okay, determine the optimal order of this constant. So so this is another result. Okay, so this in fact we can compute this constant alpha PQX by some root constant C, and maximum, you see the maximum P to power 1 over Q, and P prime of course is the conjugate index of P. So this odd, then we have, this is linear dependence on the martingale cotype Q constant. Okay, so this factor, the maximum p to power 1 of Q and p prime is optimal when p goes to 1 of infinity or infinity. So we have determined the optimal order of this constant for the cotype case. Of course, we can ask the same question for the type case, but for type case, the question is not very clear at the moment for me. So there's still some problem left open in this direction. Even in the classical case, when I search for such optimal orders, when I was working on this based constant, I also asked, in fact, I realized even in the scale case, when X is a complex number C, not all based constant has been completely determined the optimal order. I have several exchange with Asserts now. So he told me he also looked at this, searched this, looked for in the literature, but he didn't find any relative work. Okay. So even in the scale case, some cases are still unsolved. Okay. So this is our main result. Now I would like to give you some idea of proof. So I just remind you the main theory here. Okay. The main theory here. So in fact, the proof, the most technical part of the proof is that on the cotype case, this is part 1. We have 2 parts. Part 1, first one concerns the Poisson semigroup. The second one for the semigroup itself. Okay. So in fact, the most difficult part is the first one. So we have to prove this inequality. For example, if X is of martingale cotype Q, then we have this upper estimate on this Q variant of the square function. Okay, Q variant of square function, we have to do this one. So this is the Q variant of the square function. That means we have to compute the epsilon of this GQ P of F by the epsilon of F itself. Okay, So this is the most difficult inequality in the proof. So before giving you some details on some idea on proof, so I just first present to you some ingredients of the proof. So we have to use this dimension theorem, and I will show you later to transfer a general semigroup to the translation semigroup on R. So you will go back to the translation semigroup on real line, then we can use tools from harmonic analysis. So this is why we can use the so-called Carpion-Zygmunt theory. Okay. This already appeared in my first paper on this theory. Okay. Then we use this some modern treatment of Littlewood-Paley theory, the classical Littlewood-Paley theory by Wilson. Okay. Of course, because this you can imagine. So we have 2 families of inequalities. So one family is for martingales and another one for semigroup. So we have to establish a link, a bridge between so semigroup and martingale inequality. So this is so-called Bergholder-Gandhi martingale inequality. And finally, so I just mentioned the cotype case of the first part. For the remaining parts, for the type case, and also for the semigroup itself, we will use the Macintosh holomorphic function calculus. Okay. So I used last minute to give you some more ideas. The first is the so-called dimension theorem, Fentanyl. Okay, so we have our semigroup TT. Okay, we have our semigroup TT. So this semigroup can be dynamic to a semigroup, a group. You see, now is a group of positive isometrics on a large LP space. You see this TT theta. Okay. So here D, so is the embedding. So we have this LP of omega is smaller than LP, is a subscript of LP of omega theta, and P is just conditional expectation. So the projection is something of conditional expectation. So we have such a dimension theory, Fentanyl. Okay. And this dimension allows us to use coefficient with transference principle to reduce the general case to the case of the translation group. This is tau T on R. The translation group is a very good group. So everyone know how to manipulate the translation group on R. So this is the first step of the proof. So this is quite in some sense elementary. Okay.
But isn't this a diffusion now?
Sorry.
Isn't this a diffusion now? Since you reduce to the tau T, it's a contraction in every LP now, right?
No, tau P is just say again.
So since you reduce to tau T,
yes,
this is a diffusion. It's a symmetric diffusion. So it's
tau P is not a diffusion.
Oh, it's okay.
For example, tau P is not analytic.
I see. Okay. Okay. Yeah,
So
sure.
this is not symmetric.
Yeah. Okay.
It's not symmetric. Okay, it's not. So your value is not analytic. Okay, not analytic. But we will consider only in this further part. We consider only the Poisson group. Okay, you see the Poisson group. So this the first one is just we consider the. Let's show you all the page, the whole page. So we consider the Poisson semigroup subordinated to the translation group on R. We consider so this is our kernel in some sense. Okay, we take the partial derivative on T, then we multiply by square root of T. We can represent this as a convolution operator. This is phi T convolution with X. Now the function phi, you see this is the function phi is given by this, the Fourier transform of the function phi is given by this formula. Everything can be computed in this case. You see for the semigroup, the translation subgroup, then this everything can be explicitly computed using one. And also this function phi, very of course is infinity is smooth, and also satisfy this estimate and phi and also his derivative. Okay, so from this, so you can see, so our Q variant of this square function can be expressed as a Cartman-Zygmunt singular linear operator, but with a vector value kernel K. So K is given by this function phi, which now is a vector value, and K satisfies the usual standard regularity condition. So this is very good. This is very good CZ operator. A very good CZ operator. Then we can use two from harmonic analysis. Yes.
I don't see that the kernel is vector valued.
Now this you have to take the echelon.
Yeah, but phi itself is just normal.
No, this, not yet. because we have to take the integral on t. So we have to take the epsilon. For example, we can see this we have to take this. We have to take this one, the epsilon. Okay. Now in fact the kernel Kx is the convolution kernel. Kx is for any x k for any x maps to, in some sense, to the function t or in this case OK is in phi t or in some sense this OK this is one. To this one.
Yeah,
so this is considered as a function. So this is a function on a Q.
Yeah.
Okay, this is a function. So this vector value, this is the vector value. Now the vector is, now we don't have x is a Q space, is a Q space. Okay. So this is again quite a standard. Okay, quite a standard. The again some more details. So now we have to use martingale inequalities. In fact here the martingale we used are the so-called diagonal martingale. So now we use Wilson's treatment of Littlewood-Paley-Stein to reduce our inequality, cotype Q inequality, to a martingale inequality. So this shows the martingale cotype Q implies the Newton cotype Q relative to the Poisson semigroup. So this finishes the part. You see the proof of the part one on cotype case. Okay. The last one, so the remaining case we have in part one we again have the type case. The type in some sense this we have to use duality. Okay. Like for the martingale type and cotype. So the type and cotype are in duality. In duality, that means X is martingale cotype Q if only if the dual space of X is of martingale type Q. Here again we have the same situation. We use this duality. When we use duality, we have to use the Macintosh holomorphic functional calculus. So this is the first finish the proof of the first part. The second part, so the passage from the Poisson semigroup to the semigroup itself is also done by means of this holomorphic functional calculus. Okay. So this is the outline of the whole proof. Okay. I stop here. Thank you very much.